and birational geometry. So let's start with affine a symplectic variety. Yes. This is just a normal variety, a fine normal variety, such that on the regular locus of X, there exists a holomorphic symplectic form. And if you take some resolution, then that two form regularly extend. This is the definition of symplectic variety. And assume we have a crepant resolution or symplectic resolutions, then we have assumed that pi is a symplectic resolution. This means that this is a birational projective map, and y is smooth, and omega y is also a holomorphic symplectic 2 form of y. Y is smooth, and it is just a pullback of this form. So assume such X has such symplectic resolution. Okay, then and assume, furthermore, assume in this talk X has a good sister action. Sister acts on X with positive weight. This is the same as the Canadian's talk. So X has some unique fixed point and weight are all positive, and omega X is also positively weighted. So omega lambda star omega is just something weight. Yeah. L is omega. Yes. Then this sister action naturally extends. One can prove that this sister action extends to the action on Y. And we have a good situation as Canadians talk. So, but if you start with such a symplectic form, you can have a natural Poisson structure. The Poisson structure. So these varieties are Poisson varieties. So now we can consider they are Poisson deformations. The topic of this talk is just the Poisson deformations of such things. So one can consider Poisson deformations. Of X and Y. Now there is a general theorem. The statement is as follows. There exists sister equivariant commutative diagram of universal Poisson deformation of X and Y. The diagram is as follows. Can you look? Can you look here? Okay. So the diagram is like this. Here you have AD and okay, X, and you have the central fiber is just X, and the central fiber here is just Y. Okay, and this is original pi. So this means that this is a universal Poisson deformation of this, and this is a universal Poisson deformation of Y. So you have some relative Poisson structure here and relative Poisson structure here. And here, this map, this is a affine space with the same dimension D, say D. And moreover, this pi star is finite Galois covering. With a Galois group, say H. Here, universal means the following. What is a universal? Of course, this is a Poisson deformation of X. So that here you have an original Poisson structure here, and the relative Poisson structure here is just extending of the original one. And moreover, if you have a arbitrary Poisson deformation of X, so say X prime, this is an arbitrary Poisson deformation of X, and assume T is Artinian based. Then universal means that there exists unique map to the base space AD. So this is a unique map. And this family is just a pullback of this family. So this is just a pullback here. This is the meaning of universal. This is the same as the pro-representability of the Schrödinger's work. This is universal, very strong. Usual situation, this is semi-universal. This is not unique, just unique at the tangent level. But in our case, this becomes universal. Okay. So, the natural question is this. How to prove that a given diagram is universal? In many cases,
I mean, you're stating the theorem with affine space, AD.
Yeah,
so that means you're saying there's a kind of Courrenicy space for the problem.
Yeah.
And it's unobstructed and so on.
Yes, yes, yes. It includes unobstructedness. And yes.
D.
D. D is some dimension, the modular number. D is just the dimension of, in our case, this is just second batch number. Here. This is a smooth variety. Okay, so in many cases, we already have some canonical diagram. So this question is very natural. For example, I will explain, the aim of this talk is just to explain how to prove that. So the typical and simplest but essential example is the following. If you start with complex, simple reed loop, and let G be its Lie algebra. Okay. And fix some maximal torus and take its Lie algebra T. So and fix some Borel subalgebra, Borel subgroup containing T. Borel. The situation is like this. This is G. G is just this, and Borel is here. Yes, this is Borel, and this is the maximal torus. Here, this is the maximal torus. The situation is this. Okay, then we have a following commutative diagram. This is some adjoint bundle. B. B is just the algebra of the Borel. And so B acts on B by adjoint action. Then you get a joint bundle over G mod B. So you have this. And here you have G. From G to on T, while group naturally acts. W is a while group. Then T mod W. There is a joint quotient map. This is nothing but a joint quotient of G. G acts on G by a joint action, and you can take the quotient. The quotient is nothing but T mod W. Okay, so and you have a map here and here. You have a following commutative diagram. This is a famous commutative diagram of Brice-Cohen, Grothendieck-Brice-Cohen. Okay, and fiber is just the central fiber is just a nilpotent cone. N is a set of all nilpotent elements in G. This is called nilpotent cone. And by using constant Kirillov form, it becomes a Poisson deformation of N. And what is the central fiber? Central fiber over here. The central fiber is just a cotangent bundle of G mod B. And this also becomes a Poisson deformation of the cotangent bundle. And here you have a Springer map, say pi. This is a usual Springer map. And the cotangent bundle resolves the nilpotent cone. Okay, so we get natural commutative diagram of Poisson deformations. So the aim, then the question is how to prove that these are universal. This is the main question. So the first, this part, G times B, the joint bundle over T is universal at 0. The proof, the rough sketch of the proof is as follows. It's very easy because it is just smooth deformations. So you have some relative two form here, This is just a symplectic deformation of the cotangent bundle. So you have a symplectic 2 form coming from constant Kirillov. So by using this relative 2 form, you can define the period map. So the basic idea is use period map. The period map is defined by this omega. So for each point t, you get the holomorphic symplectic 2 form. So you have a period map from base space to the cohomology group of this H2 T star G mod B C. This is a C infinity trivial fiber bundle with typical fiber here, typical fiber of this. So if you take T and then you can associate its second cohomology class, this gives a period map. But this is naturally identified with the dual space of T. And this P is just isomorphism induced by constant Kirillov. Filling form. This T and T star are naturally identified by using Killing form. So this period map is proved to be the just identification by the Killing form. So this is isomorphism. So it's rather easy to show that it is universal. So the point is the next step. What is the? How about this? The second step is this J over T mod W is universal at 0. Okay. How to prove this? Here, birational geometry comes in. Proof. Use birational geometry. How to use birational geometry? I will explain this. So you have a diagram here. If J to T mod W T. So take its fiber product. This J. Then this variety. This variety gives a simultaneous resolution of this pullback family. Yes? So this is the simultaneous resolution. And it's we call this YB because it depends on the choice of Borel subgroup. And so YB gives a simultaneous resolution. This, in particular, this is a Creepant resolution. Okay. So, and we call YB is just a cotangent bundle. This is just a central fiber of this family. This is just YB. Okay. So first of all, YB is a Creepant resolution of this family, this variety. Okay. Okay. But here you please consider the following question. How many different Clipant resolutions do we have? This variety depends on the choice of B, as I said. So if you take another Borel subgroup containing T, for any Borel subgroup containing T, you can take YB prime, just as this. Then it gives also Clipant resolution of this. So one can check that the following proposition: every Clipant resolution of T times T mod W K has the form, this form YB prime. B prime is any Borel subgroup containing T. Okay. So by using the cone theory of birational geometry, one can understand the situation of those things. So let's consider the space of divisors. This is just the YB R. This is nothing but the
the equation parameter is the second commodity lesson.
Pardon?
The equation parameter is the second commodity. But each part is a proposition question.
Yes.
But in case is the 22 dimension.
No. In our case, this is just a affine case. So K3 case, just, you have a Hodge decomposition like this. But in our case, such thing doesn't exist because we start from affine. So we consider that yeah. Okay, so just consider this space, second cohomology space. This is nothing but Picard group tensor with R. Okay. But this can be identified with T R star. You have a T, the Lie algebra corresponding to T, the original T. But T has a natural real structure and take its dual. So this space can be identified a dual space of TR. Okay? And while group naturally acts on this space as a dual action. So now we have a W acts on here, and you get some while chambers like this. But each chamber correspond to ample cone, the nef cone of these Clipant resolutions, B prime. So here you have an ample cone corresponding to the original B, but here you have another ample cone corresponding to another Borel, like this. And while chamber is just a fundamental domain for this action. So each ample cone moves to another one by the action of W. This is the situation of this Clipant resolutions. We will use this. Okay. So now let's apply our theorem to the original Cripant resolution. Original Cripant resolution is just the central fiber is here. So original Cripant resolution is just YB. This is nothing but the cotangent bundle of a flat variety 2n. We call this map pi. Yes, this is just a Springer resolution. Okay, but we already know that this is a universal one by the argument of period map. So by applying theorem, we have the following situation. This is the base space T, and you have some universal space of this one, but by using this theorem says that the universal space of the Poisson deformation of X is just given by the quotient of T by some group, finite group, say H. H is just a Galois group of pi star. So you get the following picture by applying theorem. And of course, the central fiber is just N and YB. Like this. So, but we already have a following family. So we have another family here, J over T W. What is the relationship between this and this? This is also a Poisson deformation of N. So, but by the universality, this map factorizes through T mod W. So, by the universality, this map should factor through this space. So this means that H is contained in GL T, and this is a Galois group, and H contains the original Weil group. And we have a following commutative diagram. YB, the following commutative diagram: T times T mod W, T mod H, J to T. This is just a pullback of this family by this, and this map factorized by this. So you have here like this, J and X. This is a fiber product, and the central fiber is just N. Okay. So these are all Poisson deformation of N, and YB is a Cripant resolution. Okay. So I want to show that W coincides with H. So want to show W coincide with H. So in order to that, take arbitrary element H from here, then you have a following map. So take arbitrary element here, arbitrary. and pull back the family. This, so I can take G to T times T mod H. G, this is H times identity. And here you have family X. And by pulling back this clippant resolution, then you have some pullback. But it also gives a clippant resolution of this variety. But by using the previous proposition, this should be coincide with, this is just YB. Sorry. So by the previous proposition, this is just YWB. W is some wild group. Because any clippant resolution of this variety should be the form of such things. Some B prime. Okay. So by using this W, one can we have a following commutative diagram. YWB to T times T mod H J to T times T mod H J. This is just the W times identity. This is T times T mod H J. This is the H times identity. And this is YB. Okay. So so if you take a first projection from to here and first projection here, you have a following picture. WH times identity. Okay. Anyway, you have a following situation. T and YB, and here you have a original YB. Oh yeah, YB and T. Yes, and this is given by WH by WH. But this is a universal deformation. This is a universal deformation of YB. Both are universal deformation of YB. But if WH is not identity, you have two different universal families. It is a contradiction. So by the universality, this is just identity. Universality implies that WH is just one. So the arbitrary H is just given by W inverse. W inverse is contained in W. So any element is contained in W. This is the argument of main argument. So this is the simplest case. But more general case, I will not explain in detail, but this is the general case. So if you start with arbitrary parabolic subgroup containing maximal torus, then you have a following generalized Springer map. And its image is just some nilpotent orbit closure of K. Okay. It's not necessarily birational, but assume this is pi is birational. Then it means that pi gives a crypant resolution of bar. In this situation, one has a similar commutative diagram like this. Anyway, it is something like this. P R pay to TP. So this is a some total algebra, and G times R pay and TP mod out W prime. And this is a solvable radical. Solvable radical of pay. Okay. And take its normalization. Then this is the Poisson deformation of the original. Take its normalization. Then this is just the central fiber is just 0 or tilde. And its central fiber is just cotangent part. And you have original pi. So both of them are Poisson deformation of tilde and T star G mod P. Okay. The same method works. In this case, also, it's very easy to show that this is a universal Poisson deformation of this by using period map. But how about this? On this, W prime is something like some substitute of while group. I don't explain in detail, but anyway, this is something like T in the previous case, and W prime acts on TP as a substitute of while group. Okay, but here you have a TP also has a real structure, and take its dual space, then it identified with this. We call this YP, and we call this YP, big YP. This is YP. Then W prime acts on this space. Okay. So what is a wide chamber? Wide chamber is just a fundamental domain of this action. But each chamber corresponds to... so in this case, we also have the similar proposition. Every crypant resolution of the fiber product T mod T P times T P W prime, this one has the form some Y P prime. Here P prime is some parabolic subgroup containing T, but with a fixed Levy part. P prime should have the same Levy part as the original P. Such P prime, we choose such P prime, then every crypant resolution of the fiber product has the form P, YP prime. Then each chamber corresponds to, in such general case, it doesn't correspond to ample cone. It's just a movable cone. So YP prime. So each chamber is a movable cone, like this. And movable cone is decomposed into some ample cone of different. Okay. Such structure, such picture is enough to prove the universality of this family. So this is the application of birational geometry to Poisson deformations. Okay, I will stop here.